This video is the introduction to the power series. A power series is a series of the following form. So n goes from 1 to infinity, and the general term of the power series is c sub n times x to the power n. Well, let's expand the series. Let's look at its terms to get a better idea of what kind of series it is. So the first value of n is 0. That means that the first term will be c sub 0 x to the power 0. To obtain the next term, I will let n equals 1. So c sub 1 x to the power 1. Next, n is 2. C sub 2 x to the power 2. Plus, you got the idea, right? C sub 3 x to the power 3, and so on and so forth. Now, what we have here is the following. So first of all, c sub 0, c1, c2, c3, in general c sub n, represents coefficients. So these are the constants. These are the coefficients of the series. And now besides that, we can see how each term contains x raised to a power. Well, what's interesting that here x is a variable. In all the series that we have worked with so far, there was only one variable, and that variable is n, right? So n is the variable that takes values 0, 1, 2, 3, and so on and so forth, so positive integers in this case. But now, besides that variable n, we have another variable, variable x, and variable x can take any value. And what else we can see that each term is the power of x. Right? X to the 0 power, x to the power 1, x to the power 2, and so on and so forth. And you may remember from algebra that functions of this form, they're called power functions. And that's where the name of the series comes from. So it's called power series because each term is a power function. So I added this note here. Now, before we move on, let me just rewrite this expanded form of the power series with simplifying the first term. Well, actually, it's the second as well. X to the power 0 is 1. So it means that the first term is simply constant c sub 0. And then, of course, x to the power 1 is just x. So c1x. Like that. And then the rest of them are the same. Okay. And now here's the important fact about the power series. A power series may converge for some values of x and diverge for other values of x. We already said how x is the variable, so it can take different values. Well, for some values of x, this power series becomes convergent, and for some values of x, the power series is divergent. Let me illustrate that. We're going to do the following example, where we're going to let c sub n be equal 1 for all n. That means that all the coefficients are 1s, which means that we don't really need to write them. So then the power series becomes, well, that's going to be the form. Power series, n goes from 0 to infinity. 1 times x sub n, or of course I can just drop 1 and say x to the power n. So if I expand it, it's going to look like this. X to the power 0 is 1, x to the power 1 is x, x to the power 2, x to the power 3, and so on and so forth. And once again, depending on what x value is, this series may converge or it may diverge. For example, let x be equal 3 over 4. Then the power series has the following form. It goes from 0 to infinity. Instead of x, I'm using 3 over 4. 3 over 4 to the power n. Now, what can we say about the series? Do you recognize it? Well, it's geometric series. Is geometric series. And what can we say about r, the common ratio? Well, r equals 3 over 4, which is between -1 and 1, right? So what does this mean? Well, that means that the series is convergent. So the series is convergent, right? Well, how about we try x equals 2? Now let x be equal to 2. Well, then the series becomes 2 to the power n. And that's also geometric series. With the common ratio r being equal to, and that is greater than or equal to 1. And we know that with geometric series, if the common ratio is greater than or equal to 1 or less than or equal to -1, then the series is divergent. So the series is divergent. And now we know what it means that a power series may converge for some values of x and diverge for other values of x, right? Let me expand on this topic a little bit further and show you more general form of the power series. Here it is. Notice how instead of x to the power n, we have x minus a to the power n. And we can always obtain that basic form of the power series that we already looked at by letting a be equals 0. So that was just a special case of this more general power series. In different resources, this power series is called differently, but these are the most common names. A power series in x minus a, or a power series centered at a, or power series about a. We already talked about how for different values of x, the power series can be either convergent or divergent. Now we're going to expand on that, and we're going to say that every power series has an interval of convergence. And that is the set of values of x for which the series converges. So there are different possibilities of what the interval of convergence can be for a specific series. And we're going to go over all those cases. And the most logical case is when the interval of converges, well, an interval. I'm going to use those number lines to generally describe how the interval of convergence can look like. Well, before I have to point out that every interval of convergence is going to have a center. And what that center is going to be? Well, if we read one of the names that we use for this power series, the second one, see how it says power series centered at A. Then we're going to see that constant A is considered to be the center of the interval of convergence. So I'm going to put A over here. Now, since it's a center, it's going to be right in the middle of the interval of convergence. And let's say the interval is from here to here. Now, notice that I'm using brackets. And the interval itself is right here, all those values. So what does it mean that I'm using brackets here on both ends? Well, it means that interval is represented by all those values of x in between those endpoints, including the endpoints themselves, right? So endpoints are included. Now, for three other options I'm going to show here, the only difference will be whether endpoints are included or not. So we'll just consider all possible cases. For instance, so A is the center. Now I can have interval where endpoints are not included. Well, what it means that if the power series have this kind of interval of convergence, it means that the series converges for all values of x in between those numbers, not including the numbers, the endpoints themselves. So it means that at those values where we have the endpoints, the series will be divergent. So it's only convergent in between, not including the endpoints. And of course, I can have a different combination of endpoints. So in other words, I can have interval where the left-hand side endpoint is included. So it means that the series converges at that value, but it diverges at that endpoint. And it converges everywhere in between. And then I just can switch the sides, so I can say that the interval convergence is such that it converges everywhere or for all those values of x that I highlighted, including the right-hand side endpoint, but it's divergent at the left-hand side point. So these are all possible cases when the interval of convergence is an interval. Now, what else is important here is that besides the center, the interval of convergence also has a radius. And the radius is, well, exactly how you think about it. So if A is the center, what's going to be the radius? Well, the radius is going to be this distance, and we denote it by capital R. And R is called radius of convergence. So each interval of convergence is going to have a center and the radius. This is how we can describe this all algebraically. We can say that the series converges for all x, satisfying the following inequality. So absolute value of x minus a is less than 0. Remember, that's the same as saying that x minus a is between negative r and r. But now if I solve for x, right, if I add a to each side, then I'll find that x is between r plus a, or I can say a plus r, and then a minus r, right, if I add it on the left. And now look at that double inequality. It should now make sense. This should now make sense. We're saying that the interval of convergence is described by all values of x that are in between a minus r and a plus r. Let's see if we can recognize it on the number line. Well, if I take a and add r, remember r is the radius of convergence, so if I add r, I'm going to end up here. And if I take a and subtract r, I'm going to end up here. And that gives me the endpoints for the interval of convergence. Now, that does not include cases where endpoints are included or not included. So, in other words, the way it's written here, endpoints are not included. But those two inequality symbols I can change to less than or equal to, and then less than or equal to, or only change it on one side, and that will correspond to one of the cases we looked at. So once again, that's when the interval of convergence is actually an interval. But there are two other special cases. One of them is when the series converges only at its center, A. So here's A, and we may come across series that only converges at that one number, and it diverges for all other values of x. And now it should make sense, well, if that's the interval of convergence, just 1 point, one value, then in this case it should make sense that r equals 0, radius equals 0, right? And then the last special case is when series might be convergent for all values of x. So I can still show the center, A, but then I have to highlight the entire number line. So the series converges for all values of x. Well, then what is radius? The radius will be infinity. We write that r equals infinity in this case. So that's the idea of the interval of convergence. And we will be using all that information when we're going to be asked to find an interval of convergence for a specific series. So for example, we might be given a series like that. Well, it's the power series, because notice how here we have x minus 1 raised to the power n. Every series that involves x raised to power n is the power series. And we need to find the interval of convergence. We're not going to be doing this example right now. It's going to be in a separate video, but I just want to show you what's coming up. So we will need to find the interval of convergence, and it's going to be, one of those cases. And besides that, it would be good to also state what the radius of convergence is. But once we determine the interval of convergence, then it's not going to be that hard to determine the radius after that.